Hello, Chem 1B. This is Chapter 20, Lecture Video 8. We're going to be talking about fission a little bit more. So, specifically the nuclear reactor and the nuclear power plant. It generates about 20% of all electricity in the United States as of about 8 years ago. When I wrote my dissertation was when I cited this line. So it's probably a little bit lower, but I'd still bet we're still above 15% of all electricity in the United States is generated from nuclear power. So we're going to need to do something about our electricity needs in the future, especially with our needs to be concerned with greenhouse gas emissions. A lot of the rest of that 80% comes from oil or coal, both of which have a dramatic impact on global warming and climate change. So that is one of the pros of the nuclear reactor. So let's talk about some pros and cons. Now, I'm totally for increasing our amount of nuclear power in our country to supply our electrical needs. Now, I'm just telling you that up front so that if anything of my own bias comes out, I want you to be aware of it so that you can, research for yourself and make your own decision. The answer is that we're going to need to make a decision about this eventually, regardless. So probably in our generation. One of the biggest pros, as we saw in our calculation problem in the last lecture video, is the enormous amounts of energy that we can generate from very small amounts of fuel. This is very useful, especially in a technologically advanced country where our electrical demands are just increasing as we become more technologically savvy. One of the biggest benefits to nuclear power, other than the fact that it creates a lot of energy, is that it is greenhouse gas neutral, meaning it does not affect climate change, and that's a significant bonus. However, there are some major cons, and these are kind of the summary pros and cons. There are more pros and there are more cons. These are just the main ones. The cons, obviously the biggest one, which I'm sure many of you have heard of, is they can melt down. Which causes a release of radioactive particles into the atmosphere. This can cause lasting damage to the area and be very harmful to the people in the area or the wildlife in the area as well. I will say that current meltdowns have been due to human error, either on the government's part in the case of Fukushima, not re-updating the infrastructure of the power plant so that it could withstand earthquakes and tsunamis, and then on top of that, 2 Mile Island and Chernobyl, both of those have been due to people doing things they shouldn't have been inside the reactor. One of the biggest cons that a lot of people don't understand is that the waste is radioactive and it needs to be stored for billions of years generally. So this is a problem that we're going to have to deal with whether we switch towards nuclear power or not, because currently we've been running nuclear power plants for about 70 years now, or a little bit less than that, and we've kind of built up quite a large amount of waste that is radioactive and needs to be stored or sent into space or something. Those are some of the ideas I've heard. Sent to the space one kind of makes me laugh, but this is something our generations will need to do, because currently all waste is stored on site at the power plant, which is not what it was meant to do. The storage units there were supposed to be temporary. They're now becoming long-term. And in addition, it is a little bit of a hazard to store the waste in the same place you make the waste. So this is a cool picture. This is a picture of a reactor turning on. The blue light you see emitted is Cherenkov radiation, which is due to the water that's surrounding this reactor as it heats up. It's very pretty. I've seen a reactor turn on before at UCI. I got to stand right about where this picture was taken. You're like 20 feet above the reactor, and it's all water between you and the reactor. It's very pretty, and it's pretty crazy when it does turn on. Let's talk a little bit about how a reactor works, and this is always one of the funny things. I always see like news people, they have no idea what nuclear power is all about. If you ever seen a picture of a cooling tower with like this big white cloud coming out of it, I've like online, if you just Google it, there's so much misinformation about that. I've seen things like, oh, that's a big cloud of CO2. It's totally polluting. It's toxic. Watch out. Oh no, it's steam, just water vapor. Um, Basically, how these cooling towers work is they run water through the heated steam in the turbine, which recondenses it, and then that water then heats up and comes out of the tower as a big cloud of water vapor. What a nuclear reactor, a fission reactor at least, is basically a giant water heater. We have the reactor rods here. They heat up a liquid that they're stored in. That liquid goes through a container filled with water. The water, due to the high temperature of the pipe going through it, turns into steam. The steam turns a turbine. The turbine turns a generator. The generator creates electricity. Then we have our cooling tower recondense the steam, turning the turbine back into liquid water and goes back in and repeats. It's pretty neat process. So yeah, let's continue on. So just to kind of give you an idea of an average output of energy, the average output of coal is about 5 times 10 to the 7 joules per ton. Whereas, like we just calculated, 1 mole of uranium-235 releases about 1.49 times 10 to the 10 kilojoules of energy. We want to find the number of tons of coal required to produce the same amount of energy as 1 gram of uranium-235, right? So let's figure out how much energy is given off by 1 gram of uranium-235. So far, we have 4.9 times 10 to the 10 kilojoules per mole of uranium-235, right? So I need to take this guy and go, oh, well, I want to cancel moles. 1 mole of uranium-235 over the molar mass of uranium-235, which, like we saw on that slide a couple bits ago, was 234.99 grams. I'm rounding a little bit. But if we do that calculation out, we get how much energy per gram is required, or is given off, right? So 1.49 times 10 to the 10 divided by 234.99. This gives me 6.34 times 10 to the 7 kilojoules per gram. Now, it may look like these numbers are very similar, but there's 2 distinct differences. This is 1 gram of uranium-235. This is 1 ton of coal. Lots of coal there. And this is in kilojoules. This is in joules. So if we want to figure out how many tons of coal we'd need in this case to do 1 gram, well, we know the amount of energy released here is 6.34 times 10 to the 7 kilojoules. Let's change that to joules. There are 1,000 joules in 1 kilojoule. This gives me back to 6.34 times 10 to the 10 joules. And if I want to figure out how many tons I'd need, I need to divide this by 5 times 10 to the 7 joules per 1 ton of coal, right? So if we do that out, you get that you'd need about 1,268 tons of coal. That's how much tons of coal you'd need to get the same energy output as 1 gram of uranium in a nuclear reactor. I don't know. I thought that was a fun calculation to kind of show you how much energy we can get from such a small amount of a sample. And the comparison to typically our next most energy source in the US at least, which is coal. All right, so let's talk about the other major possible energy source from nuclear power, which is known as fusion. Fusion is basically what's going on in the sun. So if we could create a fusion reactor that was viable, that would be extremely useful. What is fusion? Fusion is where It's kind of the opposite of fission. So in fission, we take a nucleus, we hit it with something, and we break it apart into small pieces. In fusion, we take two nuclei and we smash them together really hard and hopefully combine the two nuclei into a new, heavier one. So we fuse the two nuclei together. Both processes, fission and fusion, release significant amounts of energy, which is pretty neat. Research is definitely being done currently on a nuclear fusion reactor, and we have fusion reactors out there for research purposes, but not for power purposes. And the problem with a nuclear fusion reactor currently is the crazy high temperature you need to get the reactor up to in order for fusion to occur. Right now, if you think about the sun where fusion occurs, the center of the sun is where it's occurring, and it's pretty hot there. So in order to get fusion to occur at a reasonable temperature, a lot of research being done in this in what's known as cold fusion. And that's kind of a misnomer. It's not like we're trying to make it ice cold and still have fusion occur. It's more that we're trying to reduce the temperature that fusion can occur at so that it becomes more energetically viable, right? Because if you have to heat up a reactor to a really high temperature, you're using a lot of energy to do that. The energy you get out needs to be substantial in order to counteract the amount of energy you put in. So there's a net gain. If we could get fusion to occur at the same temperature as fission, it would generate about 10 times that of fission. So it's definitely something that should be researched. It's just still quite a ways off. So again, sun is where fusion occurs. Like we can have fusion occur on our terms, but this is a very good example of fusion. Here's a real life research fusion reactor, and you can kind of see the perspective here. This guy, I don't know how tall he is. I assume probably 5 to 6 feet tall, and about 3 of him gets you to the top of the fusion reactor. But it's a cool fusion reactor. It's for research purposes. All right, as always, if you have any questions, feel free to email me or come to a discussion session. This is the last lecture video for chapter 20. So